I'm a geologist and I work for the Victorian Geological Survey. And my main background is in structure and tectonics, but because I've done a lot of regional mapping, just making new geological maps, kind of forced to just be a jack of all trades. And so that jack of all trades background is partly what got me into this story, which is around sorting out the landscape evolution of parts of Victoria and uncovering some really big surprises that are more or less hiding in plain sight. And some of these things have been landscapes in the state, which I've never really understood and I've always wondered about them, but didn't know where to start solving them. And I think that's actually pretty common. Reading through the literature, there's lots of people who've scratched their heads around some of these landscapes. And in a way, the solution is obvious in hindsight, but it's such a big step that people were just not keen to take it, I think. I think that might be the reason. So I'm here today to talk to you about using Permian glacials and glacial landscapes and also PETM regolith as time markers to try and understand what's going on with the uplift history and landscape evolution of the Victorian Alps, and the Australian Alps is part of that, and it ended up being the whole of the state. And so it's got implications for Victoria, New South Wales, and potentially also South Australia and Tasmania and Western Australia as well. Now, why is this talk not advancing? Here we go. So obviously I'm talking about the whole state. So we'll just pay our respects to the traditional owners of different parts of Victoria. And the cool thing about geology is it's the Earth. And so it's this gigantic story that's bigger than all of us, and it kind of unites us all. So this is the talk. So I've got an hour. So I've actually fleshed it out a little bit more from the 20-minute talk I gave at the ARGA convention, which is it was a challenge getting through all this stuff in 20 minutes, and you'll see why when you see the talk. So what I'm going to talk about here doesn't matter. It's just so that you can see where we are in the talk as we're going through. So the first question is, why this? Why have we got this story? And it was really came out of the Victorian government's current quest for enhancing our critical minerals understanding. So like all the states and the federal government, governments are taking critical minerals more seriously than they did in the past. And for a small survey like the Victorian Survey, there's an opportunity there. And the Victorian government's keen to understand what critical mineral endowment we may have, and so they can inform their policy development and planning. And so we've done a whole bunch of these different reports. And these are two pertinent ones. So one was looking at the potential of clay occurrences in central Victoria to host high purity alumina and rare earth elements. And the most important regolith for that is a Paleocene-Eocene thick regolith that we've got widely preserved across Western Victoria. And we hadn't sort of aware of it, but we hadn't really looked at it in too much detail. And we were aware of a bit of a story with that regolith in terms of what it can constrain, but we hadn't really tried to apply it statewide. And now we have. And so that's part of the story. And another part was looking, for example, at rare earth elements in alkali, silicate, igneous rocks in Victoria. And so that was an interesting project. We've got some of these rocks, and some of them are Triassic, and some of them sit in landscapes and prove those landscapes are at least Triassic, and that's up in northeastern Victoria near Benambra. And with these sort of individual little bits and pieces where there's little points of time control, a wider story started to emerge. And this is what I'm going to talk to you about today. So the first thing is, I'm talking to ARGA now, so probably everybody knows what the PETM was, but I'll explain it anyway, just to make sure that everyone's on the same page. This is what it is. It's the Paleocene-Eocene Thermal Maximum. So this is the temperature we're sort of at today, and that's kind of where the PETM spike was. It was kind of 12 degrees hotter than it is today. And it didn't last long, but it was followed by a long tail of warmer weather called the Eocene optimum. And when you look at various isotope studies and whatnot, the PETM just sticks out as a huge excursion in almost all of them. So the world just went crazy hot for about 200,000 years. So the global mean surface temperature at the peak of the PETM was between 27 and 35 degrees. Sea surface temperatures in the East Tasman Plateau, which at that time was pretty much located at the same latitude as the Antarctic Peninsula, so 65 degrees south, was 33 degrees. So it was full on tropical, even though it was in the Antarctic. And so at that time, Victoria was both subpolar in terms of its latitude and tropical in terms of its weather. And that tail of that weather persisted for the next 10 million years. So as a result of that, we got some tropical type regoliths formed in Victoria at that time. And it's really significant. And the reason it's significant is because the preceding positive temperature excursion of a similar magnitude, which was the Cretaceous thermal maximum, which was 30 million years earlier, that's too old to explain the regolith profiles we've got developed on Paleocene age fluvial units in Victoria, so we can rule that old one out. Eocene strata in Victoria are also weathered, but with less intensity, and that's consistent with the Eocene optimum. Nothing younger than the Oligocene, or the Eocene really, preserves evidence of tropical style weathering, and that's not surprising because the climate more or less returned to something similar to what it is today. And there's no comparable global thermal excursion since the Eocene anywhere, so we just don't get it. So that means that the PETM regolith on its own is a fantastic time marker if you can recognise it, and it's actually pretty easy to recognise in Victoria because it's so thick. It's 80 metres thick where it's preserved in its entirety, and even where it's deeply eroded, some of the characteristics of the way the bedrock weathered in that enormously thick regolith gives the game away even when the actual soft stuff's been eroded away. So it makes it easy and unambiguous. And because of its global context and the fact that we see this stuff everywhere, we expect this event affected every rock that was exposed to Victoria at that time. So it's indiscriminate. So what that means is we can use it as a time marker for the age of the land surface. So where we've got it substantially or intermittently preserved, it dates the local land surface to the late Paleocene at a minimum, and that's 60 million years. Where it's entirely absent, it's an indication that the local land surface is younger than the PETM. So the PETM's been stripped off, and then some other bedrock as well, maybe. So it's a really good time marker. So in Victoria, we have a lot of it. So let's have a look at what it looks like. So this is a map of the whole of Victoria, and this is showing commercial PETM clay localities. Now, there's a few red dots in here, especially up in the north around Swan Hill in the Murray Basin that are not the PETM, but this is a statewide database of commercial clay localities. Apart from the Murray Basin ones, the rest of them are almost all PETM deep regolith profiles that have been mined commercially for clay. Straight away, if you look at the map, you'll see that they're all confined to central and west Victoria, and there's hardly any of them in eastern Victoria at all. And that's where all the deep incision in the Victorian Alps is. So straight away, that's telling us something as a first pass about the age of a lot of that erosion in the Alps. In central and western Victoria, PETM regolith is best preserved in river valley flanks and floors. And that's telling us two things. One, it's being preserved because river valley flanks and especially the floors are low relief landscapes where there's minimum erosion. So it's the best chance for the regolith to hang around. But also that those valley floors were formed at that time because they were there when the PETM regolith formed on top of them. Whereas in eastern Victoria, the PETM regolith is only preserved on high plateau surface remnants right up in the Alps, up around sort of 1,500 to 1,900 metres. And normally that's where it's just been locally protected under some other rock type, like, for example, a lava flow. PETM regolith is entirely absent from river valley flanks and floors, and there's very, very minor exceptions right up on the fringe of the Murray Basin there. From the heart of the Alps, there's just none in any of the valley floors. So there's a fundamental difference there. There's also a whole bunch of other little spots which aren't commercial, and I'll put them back on again, but which are nevertheless significant for the story. So I've marked a few of those extra key points to control on, and we'll talk about some of those things. So let's start in Western Victoria and have a look at what it looks like. So this is west of the Grampians. So this is Cambrian bedrock, believe it or not, but it's just been weathered to a depth of about 80 metres by this really thick Paleocene-Eocene Thermal Maximum regolith. So this is in the Black Range, and this is a bunch of survey geologists running around trying to explain to some Japanese industry people why we think this is a Cambrian volcanic arc, and they thought we were mad because it's essentially all just various sorts of clay. But once they got their eye in, they could see how we came to that story. A little bit further east, south of the Grampians now. So this is in Cambrian turbiditic rocks. This is a place called Glen Thompson. There's a brick pit there, and there's a 60-metre thick regolith profile superimposed over that Cambrian turbiditic rocks. And those rocks are essentially dipping subvertically here, but you'd be flat out even picking Betty in them. You can just see the faintest hints of layering that sort of obliquely running up that clay pit there. Near Ballarat, there's a lot of Paleocene-Eocene Thermal Maximum regolith preserved around Ballarat. It can be developed on Devonian granites. So this is Tom Andrews, the co-author for this work, looking at a kaolin deposit developed on a Devonian granite at Lalal, enormously thick regolith here, probably in the order of, again, 50 or 60 metres. This has been mined commercially for kaolin, which was used for, paint and clay, paper, pulp, and all that sort of stuff. There's another one a little bit further east. So this is near Werribee. This is a unit called the Werribee Formation at Ingliston Gorge. Now, what's interesting about this one is that this regolith is so enormously thick here, well over 100 metres, that it was interpreted to be a redeposited kaolinite. So this unit was actually pulled out as a unit that was younger than the Paleocene-Eocene Thermal Maximum. However, when you go and look at it, you can actually see that the laterite associated with the colonisation is still intact in places, and that's what this photograph's showing, a hard cap of laterite sitting on top of this big, thick kaolin profile. Well, this is a WA type photograph, but it's located sort of 30 kilometres west of Melbourne. So, in fact, this is just an enormously thick regolith profile that's developed in situ. We see no evidence it's been reworked at all. So that's the Bacchus Marsh Formation or Werribee Formation. Let's have a look in northeastern Victoria. So if you want to find these things up in northeastern Victoria, you kind of have to go right up onto the top of the Alpine plateaus. So this is up at Mount Little Higginbotham Summit, which is near Mount Hotham. So this is basically the road up to the ski field there, located about 1,700 or 1,650 metres above sea level. So what we're looking in this photograph, OAP, is Ordovician Paleozoic bedrock. And you can see it's been kaolinised. It's white now. The PA unit sitting over the top is a Paleocene age fluvial gravel. And all these rocks are protected underneath an Eocene age basalt flow that sits on top. So looking at the Paleocene age gravel, it's a pretty interesting one, this one, because it's got lots of fossil detritus in it, including leaves and things, and they're preserved well enough that they could be they could be identified. And Greenwood et al., for example, identified some of this vegetation as Paleocene age alpine vegetation. And given that it was in the middle of the Paleocene-Eocene Thermal Maximum and all this deep weathering was going on, and this deep weathering has overprinted this PA unit, that strongly implies the plateau uplifted preceded the Paleocene, because they had to get this landscape up into an alpine environment at a time when Victoria was really, really hot. A lot of these units, and there's another white fluvial gravel sitting underneath a basalt cap there, they've been protected because there's Eocene lava flows capping the tops of a lot of these mountains, and I'll talk about that a little bit more later in the talk. Let's have a look at another one, Mount Buffalo, huge plateau at Mount Buffalo. So this is looking at Mount Buffalo from Mount Feathertop. So you can kind of see the amount of topographic relief we've got here. It's in the order of 1,500 or 1,600 metres, and that's Mount Buffalo over there, a gigantic inselberg that's been surrounded by younger erosional escarpments, and it's basically developed on a Devonian age granite. This is a view from near the summit, or looking at, from one of the high points, looking at the summit of the Horn on Mount Buffalo. It's a lovely alpine environment, and you can see it's very craggy, and there's a lot of fresh rock exposed, and there's not much evidence of a thick clay regolith profile up on this plateau remnant. However, when you look at the character of the granite terrain that's exposed, you can kind of start to see evidence of what might once have been there, which has been removed by erosion. So let's have a look at these cliffs below the Horn. So this is a exposure that's about 60 metres, 70 metres high of various rocky granite tors. And if you look closely, you can see, for example, some of them appear to have toppled over there on the side. And this is giving us a clue as to how these tors formed. This is a classic textbook example of deep weathering superimposed over a jointed granite. So you have a jointed granite and you impose a deep weathering profile over it, and you end up with core stones of fresh rock surrounded and supported in a surrounding matrix of sort of kaolinised granite, and to a depth of 50 to 100 metres in places. And when you eventually uplift and erode the clay and wash the clay away, the core stones all topple because they're not supported by the clay anymore. And that's pretty much exactly what we're seeing across Mount Buffalo. And it explains a lot of the strange features you see there, gigantic tors sitting on top of other tors and things. So we infer that there was a Paleocene-Eocene land surface above this with a thick clay weathering profile that extended right down into the bedrock, and the weathering intensity just decreases gradually with depth. And you can see that preserved in the landscape. Once you have this understanding, you can start working out how big and how thick the Paleocene-Eocene Thermal Maximum regolith profile was up on top of this plateau. So here's a series of tours in a thing called the Cathedral. It's about 100 metres high. So that's giving you an idea about how thick the regolith was. It's super impressive. Once you get this, and actually once you go looking for it, you can actually find remnants of the Paleocene-Eocene Thermal Maximum regolith in all those vegetated areas. It hasn't eroded away completely. It hasn't been documented there before because no one's bothered going looking for it. It's not actually all that hard to find it. It shows up in lots of road cuttings there because obviously the road cuttings have avoided all the rockiest bits. It's just that it hadn't been previously documented because no one was thinking about it. Once we got this pattern understood at a place like Mount Buffalo, we can see this as an explanation for the landscapes on granite across a lot of central Victoria. So, for example, Cobor. That's a typical landscape up on top of the Cobor Plateau. There's regolith, all the soil is in a kaolinised regolith there, but it's mostly eroded away. And so you get these sort of 10, 15 metre high tors poking out everywhere. It's a very common feature. That's the Paleocene-Eocene Thermal Maximum, but there was also the Eocene Optimum that tailed on from it, and we can see evidence of that in Victoria as well. For example, the Eocene volcanics on Phillip Island. So this is a place called the Nobbies on Phillip Island. It's a nice spot to go. And you can see there's stacked lava flows. And the uppermost lava flows got an enormously thick red regolith profile on top of it. And this regolith profile is very extensive in Gippsland, and it's been mined for bauxite at places like Merbau because of that. And it was formed in the Eocene. And if you look at these stacked lava flows, you can see that there's thinner tropical style weathering profiles developed even in between the lava flows. And because we've got the age of some of these lava flows, we can see how quickly these things were developing. It's really consistent with, really rapid soil formation in a tropical environment. And here's an example of one of those. You can see the basalt's quite fresh, and then it's just transitioning upwards into a really thick red regolith profile. Classic tropical style weathering, the sort of thing you'd see in places like Broome today in Australia, but we've got this stuff in Victoria as well, and it's Paleocene and Eocene. Let's have a look up on top of the Alps again. So where we've got these Eocene volcanics up on top of the Alps, this is an example at Mount Clear in the heart of the Alps, and that's actually just a little remnant of Eocene lava flow sitting on top of the ridge there. There's a few others in the distance capping all these different hills. Now, because they're up in the Alps, they've had the thick red regolith weathered off, but you can still see evidence that there was a regolith there because the underlying rock beneath the regolith has been altered, typically with zeolites. And so this is an example of basalt from Mount Clear. All the vesicles in that basalt are chock-a-block full of zeolites, and they're a classic Eocene optimum regolith trace. So, for example, those sorts of alterations are completely absent from the younger basalt flows in Victoria, like the newer volcanics of Western Victoria, because the climate is temperate now. And so these sorts of tropical style weathering alterations just do not occur. Let's have a look in central West Victoria. So this is a really good place to start constraining some landscape evolution history using these regolith profiles. So this is an example of a deep weathering profile superimposed over granite. There's drilling here. The regolith profile extends down about 70 metres. The granite is the white, pale, kaolinised rock. Sitting on top of it unconformably or disconformably is a Paleocene age fluvial gravel, the White Hills gravel, and it's in the laterite part of the profile. So it's been laterized during the Paleocene-Eocene Thermal Maximum. So now we've got this characterized regolith across the state. We can understand where it is and where it isn't and what it looks like. We can start using it to understand what was happening in Victorian landscapes in the Paleocene into the Eocene. In the case of West Central Victoria, it's recording a period where it was very, very wet and erosion was locally really high. So we'll jump back to that same spot in Central West Victoria, exactly where it doesn't really matter. You can see there's a bunch of granites there, which are the sort of pink and orange rocks, and they're intruding a bunch of Cambrian age meta-sediments, which have all been tightly folded, and they're the kind of purpley rocks. And then there's a bunch of, younger alluvial units sort of draped over the top of them all. The last photograph I showed you of the White Hills gravel sitting over the granite, that was actually located here where that red dot is. And the unit on the map is PXH. That's the unit. It's a Paleocene age fluvial gravel. So straight away, if you have a look at this map, you can see there's lots of this Paleocene age fluvial gravel everywhere, all dotted around the landscape, just little bits of it all over the place. In the northwest there, it's pretty extensive, and then there's little bits and pieces everywhere else. Now, if I take the geology off and swap it for topography, what you can see with these Paleocene age gravels is that they're all sitting low in the landscape, and rising above that landscape is a plateau, high plateau, surrounded by an erosional escarpment. And because we've got these Paleocene gravels at the base of the erosional escarpment, they're providing a minimum age for that erosional escarpment. So this erosion that has attacked this high plateau, and the high plateau is around about 1,000 meters high, and the gravels are sitting around about 200 meters. So it's like 800 meters of relief here. That erosional escarpment is Paleocene because the base of it has got Paleocene gravel. So this is where you can use the regolith and the gravel as a time constraint to start working out the erosion history for older landscapes that are preserved in Victoria, and the classic example is these little plateaus. So we have an ancient uplifted alpine land surface, and this is the same one. So this plateau in Western Victoria, you can see remnants of it extending through central Victoria, and it just grades up into the Alps where it gets about another 900 meters higher at its highest point. But it's pretty much statewide. It's been attacked by erosion in Western Victoria in the Paleocene. And we know when it happened because we know the age of the gravel. And we know the age of the regolith was formed on top of the gravel. So it's a great local constraint. We've known about this one for years. What we didn't know is how to use this as a tool to understand the evolution of the other parts of the state. If we go to where that white dot is and have a look along the front of the range, it'll give you an idea of the scale we're looking at. So that gravel sitting on top of the granite with the Paleocene-Eocene regolith on top is located down there, and Bed Nevis is about 900 meters above sea level. So there's about 600 meters of vertical relief in this photograph, and there's bits of the regolith preserved on top and adjacent to Bed Nevis, but it's mostly absent from the erosional escarpments because they're too steep to hang on to the regolith. It's just fallen off. It's just been eroded away since the Paleocene. If we go back to our gravel again and look at how extensive it is, we can use this as a tool to map further west. So this is looking from Ben Nevis to the west, and you can see there's other plateaus on the horizon there, and the big one is in the Grampians in far western Victoria, and that's the Major Mitchell Plateau. That's this thing, and it's sitting up around 1,100 meters above sea level. And so it's another old land surface remnant that's been deeply dissected, and that deep dissection happened prior to the Paleocene, and we know that because there's Whitehill's gravel at the base of the erosional escarpment again, and the thick Paleocene-Eocene Thermal Maximum regolith. And that Paleocene-Eocene Thermal Maximum regolith is mostly absent from the Grampians because on the high plateaus it's been eroded away, and a lot of the other dissection has been modified quite a bit more recently, and you can sort of see how rugged the landscape is there in the Grampians. Bit of snow there, that one. So thinking about the Grampians, and this is looking at the Grampians from further south, we had an older land surface that's been dissected by the Paleocene, so that the base of it could have Paleocene gravels and regolith formed on top. But what we don't know in this story so far is the age of the uplift of that land surface. So clearly now it's 1,100 meters above sea level, and it's been dissected into the order of 700 to 800 meters deep. But when did that happen? When did this uplift happen, and how old is this land surface on top? And this is not well constrained locally, but we can look further afield to get a bit of an idea. So that's where the Grampians is. If we look further south into the Otways, the Otway Range is giving us some clues. This is quite close to the coast here. This is the Otway Range. It's quite mountainous. It's not as mountainous as the Grampians. It gets up to a bit over 600 meters above sea level. But what's important about the Otways is that, one, there's remnants of an uplifted elevated plateau here. And two, the base of the erosional escarpments that are attacking that plateau, located close to sea level, are Paleocene. So we have Paleocene rocks there called the Eastern View Formation, and those rocks have been overprinted by a thick Paleocene-Eocene Thermal Maximum regolith. So they're providing the same age constraint on the dissection of this uplifted plateau as we can see further inland in the Stawell zone and in the Grampians. What's important about the Otways is that the bedrock there is a lower Cretaceous stratigraphy group, and it was planated prior to uplift to 600 metres in the late Cretaceous, and that's constrained by the age of the rocks in it. It can't be any older than lower Cretaceous because that's the age of the rocks that form that range. So given that we've got this constraint of uplift for the late Cretaceous in the Otways, and we've got the same relationship between the uplifted dissected plateau and the surrounding Paleocene-Eocene Thermal Maximum regolith and the sediments that has overprinted, it seems reasonable that the uplift that's occurred inland is also late Cretaceous. And when we look further afield, we see the same story in the Gippsland Basin as well. The same low Cretaceous rocks, the same plateau remnants, the same Paleocene age sediments surrounding it. It's called the Latrobe Group in eastern Victoria. Same regolith though, and the same uplift history. And it probably also explains some of the plateaus in Wilson's Promontory, which are uplifted about the same amount as the ones in the Strzelecki Range. So we've got this story that looks like a planated surface that was uplifted in the late Cretaceous, and then it was immediately attacked by aggressive erosion in the Paleocene. And then towards the end of that system, it's had this thick Paleocene-Eocene regolith superimposed over the top. And this story seems quite regional. So this is our story. We've got low Cretaceous Strzelecki group planated, dissected close to sea level. The fluvial aprons and the regolith more or less prove it. So it's giving us a maximum age for high plateau uplift in southeastern Victoria and a minimum age for high plateau uplift and deep dissection in southeastern Victoria as well. So this is our map of Western Victoria. And when you look at where we've got Paleocene fluvial Whitehills gravel, the Paleocene gravel overprinted by the PETM regolith, it's kind of all over the place. So it's all those spots I showed you at the start of the talk and more besides. Generally speaking, all down in the valley floors where it's best preserved. And this is telling us something about the fact that we had a big plateau system here. It was all uplifted and it's been mostly dissected, and there's just a few remnants left behind here and there. If we have a look at the first one I showed you near Mount Cole and Ben Nevis. So this is just north of the plateau. And we have this thing called the Wimmera River that flows from the highlands at Mount Cole north into the Murray Basin. It doesn't actually really ever reach the sea. It just sort of runs out of steam because it's kind of an ephemeral river these days. But what's interesting about it is it sits in a fluvial valley system that is enormously wide. And it's filled with this Paleocene PXH Whitehills gravel unit, which has the Paleocene-Eocene Thermal Maximum regolith developed on it. So the modern river is sitting in an ancient valley, and it's a dramatic underfit to that ancient valley. So this is the Whitehills gravel I showed you in that photograph sitting on top of the granite. That's what it looks like. The valley it's sitting in is sort of pretty low angle floodplain. It's about 5.5, 6 kilometres wide. The same unit exists way further downstream. You can trace it up to the northwest for a long way. So this modern river, which is ephemeral and small, couldn't possibly have carved a valley this big. The ancient river had to be much bigger. And this is telling us something about the climate that's prevailing at the time when that aggressive erosion of that uplifted plateau was occurring. It was something more like what you see in New Zealand today, far, far wetter than Victoria is today. So the conclusions we're drawing from these landscapes, and these are conclusions we've had for a long time, is that Western Victoria was really wet in the Paleocene. Erosion of the uplifted plateau that was uplifted at the end of the Cretaceous was rapid and aggressive. The rivers that were extending away from that eroding and driving that erosion were wide and highly energetic, and they're able to deposit really coarse quartz gravel deposits, and that's what this Paleocene gravel is. The modern rivers are all underfit because the climate's changed since then. The plateau erosion's barely advanced in Victoria since the Eocene, and this changed for some reason. And I mean, the obvious reason is the rainfall changed, right? But we're trying to understand how this compares to what we're seeing in eastern Victoria, where the story is a bit different. So now we'll go to eastern Victoria, and this is a curious case of the almost entirely missing PETM regolith in the Victorian Alps. So the Victorian Alps are different. There was the same pre-Paleocene uplift. I think everyone's in agreement that the uplift here was probably pretty early, and the rocks that were incorporating alpine vegetation up in the Alps that was happening in the Paleocene. So it makes sense that the Alps are uplifted in the late Cretaceous along with the rest of the state. But it doesn't look like there was much Paleocene erosion. So for an example, this is the Eocene basalt on Mount Clear I was talking about earlier. If we think about how these basalts form, they're really mafic, hot basalts that were highly fluid when they were erupted. And so, of course, basalts like that tend to flow away from the eruption centre and just occupy pre-existing valleys, and they become valley-confined flows. And this is what we think's happened across the Victorian Alps. But when you have a valley-confined flow of basalt, it kicks the river out and it becomes a lateral stream. And then over time, because basalt's actually quite resistant to erosion compared to the bedrock that the basalt's sitting on top of, the lateral streams start to cut their way down and form new valleys on either side of the original valley, so that you get this topographic inversion where the basalt flow remnants end up sitting on top of the hills adjacent to the new valleys. And that's what we've got at Mount Clear. It's the old former valley floor, but now it's some of the highest peaks in the whole of the Victorian Alps. And they've got these enormously deep valleys sitting on either side. And by definition, those valleys are post-Eocene. They eroded after that lava flow was emplaced in a valley of its own. And you can sort of trace these things. So this pretty much proves that local deep dissection in the Alps is post-Eocene. So it's a different erosion history to Western and Central Victoria. It doesn't necessarily prove the broader Alpine uplift must be post-Eocene though. We're pretty confident it isn't. We're pretty confident that happened in the late Cretaceous, and Fons van den Berg's demonstrated a few spots where some of these lava flows have flowed down erosional escarpments which were over 1,000 metres high in the Eocene. So it pretty much shows that there must have been uplift there in order to allow that to happen locally. However, the erosion that has now dissected these lava flows is definitely post-Eocene. So it's young and it's different to Western Victoria. So there is complexity in our story here. When we look at alluvial or fluvial river profiles, this is from a classic sort of geography textbook from 1951, but it ages really well and the fundamentals are correct. River valleys are V-slots. That's how they initiate when they're juvenile. And they eventually just get bigger and bigger, and they're fundamentally constrained by the angle of stable repose of the bedrock that the river system's cutting into. And so you can see they get broader as V-slots and they get broader and broader. And when you have a look at the Victorian Alps, most of the Victorian Alps, so this is high Victorian Alps here, that's Mount Feathertop in the background there, that's the second highest mountain in the state. Most of the fluvial systems that are incising the Victorian Alps are really juvenile. They're kind of this. They haven't really matured yet, they're still actively eroding, and that makes sense because the erosion is post-Eocene and it's still ongoing. There's a few places where fluvial systems have sort of broadened to the point where they're starting to become braided plains at the valley floor, but they're sort of few and far between in Victoria. So, for example, there's that same view of Mount Buffalo from Mount Feathertop, and you can see the Ovens Valley starting to become a juvenile braid plain. So it's flattening out, it's got a floodplain at the base. Even the biggest river that we've got in the Victorian Alps, the Snowy River, is still kind of not super mature. So it's still actively incising its way down through the uplifting Alp or through the Alps. So this sort of really meets our contention that most of this erosion is definitely post-Eocene. It's actually quite juvenile, it's still ongoing, and it's different to Western Victoria. Which gets us to where this whole story took a real left turn, and that was a curious case of the missing uplifted Mesozoic plateaus of far western and west central Victoria. So going back to our map of west central Victoria, and you can sort of see at the bottom right-hand corner there's Melton, so that's pretty much the suburbs of Melbourne. And obviously we've got the Grampians there, and the western side of that map is the South Australian border. So what we have from the landscape story that we can constrain is a Cretaceous high plateau that's been mostly eroded away in an area that's sort of centred on a place called the Stall Zone and the Grampian-Staveley Zone. That's the name we give to the basement terrains here in the Paleozoic rocks. So we've got little remnants of the high plateau sort of preserved intact on top of the Grampians and on top of the Mount Cole and Pyrenees range, up around 1,000 to 1,100 metres high. But most of it's eroded away, and we know when that happened because we've got these Paleocene gravels and the Paleocene-Eocene regolith in the valley floors. On either side, though, there's no plateaus at all, no high plateaus at all. There's a few hills which have a bit of topographic relief, often a few hundred meters, like Mount Alexander, Mount Ida, Mount Macedon. It's the only one that gets up towards 1,000 meters. I think it might just get over 1,000 meters. But the rest of the landscape is actually pretty low lying. So that begs the question, has the Cretaceous High Plateau just been eroded away entirely from these areas? And we've just got nothing left. So we can use that Stall story and the Grampian story, extend it across the rest of the state, and just assume that the plateau has been completely eroded away from these other areas. And that's kind of what people have done in the past with this story. But this is where our story took a left turn, because we can prove that this is not the case. This did not happen. So what happened instead is there's some Permian landscapes that we can use to understand what's eroded and what hasn't. So these are Permian, excuse me, these are Permian glacial rocks and landscapes in Victoria. So the blue dots are areas where there's unequivocal evidence of Permian glacial till and Permian landscapes that are sitting underneath that glacial till. There's a few extra ones as well from underground gold mining, mainly from deep lead mining. And also from drilling, there's Permian at depth underneath the Murray Basin in places like the Numurkah Trough, and at depth in places like the Ovens Graben, extending into New South Wales, and also turning up in places like the Netherby Trough and the Wentworth Trough in the Murray Basin as well. And it's probably more extensive than that beneath the Murray Basin. It's just that we haven't got evidence for it because there's not that many drill holes that go right through the entire Murray Basin to see what's underneath. So there's a lot of Permian, but what's interesting about the Permian is often the places where the Permian is preserved are places where there are not high plateaus anymore. That's giving us an important control on the age of things, because we know the age of these Permian strata, that they're quite tightly constrained between about 300 million years and about 290 million years. So it's all this Permian stuff formed and was deposited in about a 10 million year interval. If you put the topography over it, you can see that the Permian is sitting in relatively low-lying landscapes in Victoria, which is really interesting because it blows out of the water the idea that there's been a lot of erosion of this high plateau uniformly across the state to form the low-lying areas. Instead, the low-lying areas just didn't go up, and they're still preserving a lot of Permian stuff. So this is an extra bit of the story that we can start to use. So where the Permian is preserved in these low-lying areas, we can be pretty confident it wasn't uplifted in the Cretaceous, and so therefore it wasn't deeply dissected in the Paleocene. And so the Permian is still preserved. And you can see in northeastern Victoria, there's some of these areas where there's a lot of Permian right next door to the high Alps. So it's sort of telling us something interesting about what that landscape, how that landscape's evolved since the Permian. So now going back to our map. So we've got this Cretaceous high plateau mostly eroded from the central part of the map, but there's no Cretaceous uplift, and there's been very limited erosion of a Permian landscape on either side. And it's dramatic because the plateaus in the Stall zone and the Grampian zone there in the centre are all now sitting up around about 1,000 to 1,100 metres, and the country on either side varies from about 180 metres above sea level to maybe about 500 or 600 metres at an absolute maximum near Ballarat. So there's hundreds of metres of difference. And the change in that history corresponds to faults we can map in the Paleozoic bedrock. And the main faults are in the west, a fault called the Yarra-Mildget Fault, separates the Glenelg zone to the west from the Grampian-Staveley zone to the east, and the Avoca Fault, which separates the Stall zone to the west from the Bendigo zone to the east. And that's in the Paleozoic rocks, and those rocks are about 500 to 460 million years old, something like that. So this is telling us that Victoria's landscape history in the late Cretaceous has experienced sector uplift. So some bits have gone up and some other bits haven't really gone up much at all. And once we understand that some bits have gone up a lot, we can start to correlate the low-lying areas with Permian preserved on them to the east and west with the high plateau remnants that went up in the Cretaceous in the central part. So straight away you start to get suspicious that the plateau on top of the Grampians and the Major Mitchell Plateau and on top of Mount Cole, these flat landscapes or these low relief landscapes, they're essentially Permian landscapes, but they've lost the tillite that could prove them. And we can see evidence for this change on the Yarra Mildred Fault. We previously mapped this, we didn't know what we were looking at. So here's an outcrop in a creek. There's a fault. It's a normal fault, and it's got Permian sitting on top of Cambrian bedrock. That's a pegmatite, gneissic rock below that fault there. It's possible that these faults are part of this Cretaceous story. So the bedrock's going up to the east and the Permian's being preserved to the west. These are spectacular Permian rocks, and they include varved muds, and you can see there's some little glacial drop stones in there as well. All the classic sort of things you'd expect to see in a Permian landscape occurring in west of that Yarra Mildred Fault there. Looking further east at these high points that are sticking out of the landscape, there's significantly prominent hills, and they've got Permian around their bases. So this is telling us that these hills, this relief is Permian. And the prominent hills, they've got topographic reliefs that range from about 150 metres up to more than 400 metres. So what are these things? This is a new way of looking at them, which I've always wondered about what these hills were and never really had a tool to think about what they might be. Let's just do a bit of a segue and have a look at some of these Permian rocks, and some awesome ones are exposed near Lake Epilogue, east of Bendigo. So this is what the tillite looks like. It's a complete diversity of crazy exotic rocks, some of which don't even occur in Victoria. They probably come from Tasmania or even Antarctica, North Victoria land. And they range from pink granites to high-grade metamorphic quartzites to locally derived rocks. Often they're faceted, and they've got striations on them from where these rocks have been ground along the bedrock and ground against each other. European geologists who first arrived in southeast Australia, because they had European backgrounds, they were very keyed into recognising glacial landscapes. They cottoned onto these rocks being glacial straight away, and they're basically correct. This is also another outcrop of them in situ. You can see a scatter of diversity of glacial drop stones and tillite there in the foreground, and you can see a big rock in the background there. It's a huge glacial erratic, weighs about 30-40 tonnes, and it's a foliated granite gneiss that it does not occur in central Victoria, so it's probably come from Antarctica, this one. And the locals recognised this back in 1861, and they gave it the name the Stranger. They recognised it was a Permian rock. And when you look at the surface, you can see it's got glacial striations on it. And it's in situ, it's sitting in a tillite of blue clay, surrounded by a whole bunch of other exotic clasts of various sizes, up to being almost as big as this one. Below the Permian till, you've got the excavated sculpted bedrock surface. So this is sitting on Ordovician age foliated metasediments. That's the bedrock in this part of the world. That's what hosts Bendigo's orogenic gold deposits. And here it's been polished by glacier, and these rocks are absolutely amazing. These glacial pavements look like they could have formed yesterday. They've just been preserved underneath the glacial till, and you can see the weathered glacial till sitting in the foreground there. The blue clay has been weathered to red in the Paleocene-Eocene Thermal Maximum regolith, but it's still managed to protect the underlying bedrock surfaces, and they're magnificent. Because there's asymmetries in the way these things have plucked, you can determine the ice transport direction, and they're consistently south to north and southwest to northeast, and that's indicated statewide. You can see some really big scour marks in them because there's quite a bit of ice on top of them. So some of the scours have been driven into fresh bedrock to the tune of like 10 centimetres or 15, 20 centimetres. So some of these features have led others to estimate the ice thickness that caused this to be in the order of 1 to 2 kilometres thick, something like that. And that's by comparison with the Holocene ice sheets in the Northern Hemisphere. I don't think it was like the Antarctic ice cap thickness. It was more like a sort of a Holocene ice cap thickness, but still extensive. And there's the Permian till sitting on top of the glacial pavement underneath. These were identified in 1895 as a glacially excavated valley, preserved in situ. And there's a summary of the work that's been done. So we've got analogues we can look at, and that's the Pleistocene sort of Canadian and Scandinavian kind of landscapes. And so I'll fall back on them for the rest of this talk. Here's our little topographic map of the area I've just been looking at with those glacial landscapes. That's the outcrop where the big erratics were preserved. That's where the Permian tillite was preserved, and and the blue shows the mapped extent of that Permian till and the landscape, the glacial landscapes around the side. So given we've got the topography, we can put a profile across and have a look at what it looks like. That's the topography. It's obviously enormously exaggerated here to show the subtlety, but you can see that where the Permian is preserved, it's sitting in a U-shaped Permian valley. That's a classic sort of U-shaped valley for a glacial landscape. Now, there's Permian glacials in boreholes east of that pointy range, and that pointy range is Heathcote. And so it kind of makes sense to join the dots, and it makes you suddenly think that the range at Heathcote, the Mount Camel range, is actually a remnant of a Permian subglacial mountain, strike ridge, sitting underneath the ice. It's been modified by subsequent erosion that's eaten away on either side of that range and sharpened it up a bit. But it sits significantly higher than all these Permian rocks we've got in these in situ glacially carved valleys. So that's what we think a Permian subglacial ridge is. So this is a new way of thinking about what the strike ridge at Heathcote is and how old it might be. The area to the west is much more complicated and dissected looking, and that's subsequent erosion. And you can sort of see it's attacked into the U-shaped valley and put a whole stack of sort of more tightly constrained V-shaped valleys on top. And a lot of that erosion looks like it's occurred in the Paleocene and even after the Paleocene, because a lot of the regolith has been eroded away from there as well. But you can also see that it's probably not enormously, it's not probably not an enormous amount of erosion, maybe tens of meters, not hundreds of meters. And that's since the Permian, which is pretty amazing because it's 300 million years ago. So once I started to characterize the shape of these valleys that the Permian is preserved in, I ran across the state and tried to find other ones. And there's in Western Victoria, there's similar U-shaped profiles across Permian-filled valleys at Tilden and Clunes and in the Loddon and Chalks Lead as well. So they're quite extensive in central West Victoria. Why are they U-shaped? Well, because glaciers are the landforms that form U-shaped valleys. So here's a landform, and that's a glacier coloured in blue. The reason the valley is U-shaped is because ice is heavy, and because it's a rock essentially, and it's flowing down and carving the valley, it doesn't just press on the bottom of the valley, it presses everywhere and scours out the landscape in all directions. And because ice is strong, even though it can flow, it can support the sides of the valley up to vertical. So even though the bedrock natural angle of repose through geological time might not be vertical, it can't collapse while the ice is there because the ice stops it collapsing. And so when the ice melts, you can end up with these sort of transient landscapes which are dramatically oversteepened, and the classic shape is a U shape, like that. Now, often when the ice has melted and the valley is left behind, it'll start getting attacked by river systems that become superimposed over the U-shaped valley, and you often get a V-slot valley, which is characteristic of fluvial deposition incising into the floor of your U-shaped valley. This is really common to see in places like Scandinavia. So if we zoom in here, we can see classic sort of U-shaped valley from a recent glacier that was really active in the Holocene, and the glaciers, remnants of it are still there in the headwaters of some of these big glacial valleys, and they're classic U-shapes. But you can also see that they're being incised by little V-shaped valleys that have formed since the Holocene. It's quite wet in Scandinavia, so some of these valleys are being eroded quite aggressively by river systems today. If you look at where the glacier extended down to become an ice cap that ran over the lower country in Scandinavia, lower relief country, it's still U-shaped though, and this is looking quite similar to that landscape that's preserved near Heathcote with the Permian glacials on top. Looking around Heathcote again, there's other features we can see which have long been recognised to be of glacial origin, and one of them are Roches Montagnais. That's what these are. These are bedrock highs that have been polished by ice on the downstream side and plucked by ice on the upstream side. And these polished surfaces have got glacial striations on them and are locally buried beneath the Permian tillite. So we know they're Permian features, and they've long been regarded as some of the best preserved Roches Montagnais in the world, just because there's not many places where you can have glacial landscapes preserved this intact for 300 million years. And these ones are at a place called Meermere, just south of Heathcote. So they have a Stoss side, which is polished, and a Lee side, which is plucked, and that gives them their characteristic asymmetry, and you can use that asymmetry to interpret the ancient ice direction. and this is how they form. So the small ones are often called roches-montagnais. Big ones can be called nunataks, and they often also exhibit a Stossel effect for the same reason, just scaled up. And often the plucking happens towards the end of glaciation when you start getting air-filled cavities, and so you can get enormous amounts of differential stress, and therefore there's a space developing that the plucked bits of rock can fall into and be transported away. And so it's likely that the landscapes like this we have in Victoria were formed towards the end of the glacial event in the Permian. And you can see the scale of these things in Scandinavia from the Holocene. They're very, very asymmetrical. So that's the direction the ice sheet was moving in the Holocene, away from the high Alps there, towards the southeast. And they've produced these asymmetric nunataks with low-angled Stoss sides and steep-angled plucked lee sides. So when you look at the scale of these things in places like Scandinavia and in Canada, it suddenly opens the possibility for something that's been hiding in plain sight in central Victoria. And that's the idea that some of these mountains that are rising above the Permian tillite deposits and landscapes in Victoria might be Permian subglacial peaks or nunataks. Now, ignore this hill. That's younger. That's a Miocene plug. But the rest of the hill, we're thinking it could be a Miocene age feature. It was formed as a nunatak. So it was formed underneath the Permian ice cap. So here's a topography of Mount Macedon. It's got Permian till-filled valleys to the west and to the south. So we can see, we can demonstrate that it's rising hundreds of meters above a Permian landscape. Now, it has been attacked by younger erosion in places, so I've had to be a little bit careful where I pick to put a profile across it to have a look at the geometry. But when you do that, you can see it's got a lower angled south-facing side and a steeper angled north-facing side. So it is consistent with the asymmetry that you see in the smaller scale Proven nunataks that occur in the vicinity in this part of central Victoria. And once I got my eye in and ran around, I started finding these things everywhere. So this is the spine of the Mount Alexander Range further north near Harcourt, just sort of kind of near Bendigo. Now, there are Permian rocks nearby at the base of the Mount Alexander Range. And so it seems reasonable that this range was rising above that landscape in the Permian. So it was sticking up as an nunatak, and actually there's a whole stack of them. It's amazing. It's a complete paradigm shift to thinking about the age of these hills and the age of the topographic relief they have around the surrounding landscape. And once we've got our eye in, these things are everywhere. So let's have a look up in northeast Victoria at Beechworth. So here's a geology map. The Permian deposits are the dark blue, and I'll just draw your attention to the one at Wurrigi, Reeds Creek, but you can see there's Permian further west as well, and that links down into the Ovens Graben, where there's a lot of Permian preserved. So there's distinct high points in this landscape, and one of them is Mount Pilot. So we're going to have a look at Mount Pilot. This is looking north, this is looking south from Mount Pilot, up on the summit, and the valley with the Permian in situ is this big valley you can see beyond that big flat slab of granite there, and it's miles away from Mount Pilot. It's like 20 kilometres, 30 kilometres away. So let's put a topographic profile across Mount Pilot and across that Permian that's preserved to the south, and then further south towards the Alps. And this is what the profile looks like there. This is where the in situ Permian glacials are, and it's a gigantic U-shaped valley. These sharper features are younger erosion, and a lot of that younger erosion is Paleocene to the west and or to the actually I've got south-north back the front there. Sorry, I've confused people there. To the north, it's probably Paleocene erosion, and to the south, it's younger Eocene erosion. But what's fascinating about this is we've got widespread terrain features here, and this is where suddenly we start to realise the sheer scale of these Permian features that are just hiding in plain sight, preserved in places in Victoria. So here's another profile in the Alps. This one is 65 kilometres long. Can you pick the relict Permian glacial landscape in this profile? We've had the lesson now. It's this one. It's the U-shaped valley. All the other valleys are V-shaped, and they're younger Eocene or post-Eocene river valleys that have dissected the Victorian Alps. But hiding in the middle of it all is this gigantic relict U-shaped valley, the Morass Creek Valley. Where's that? Well, that's near Benambra in northeastern Victoria, in the heart of the Victorian Alps. It's been one of these landscapes that's been really hard to understand. That's where the profile is located. Where the colour on the geology stops, that's the Murray River and the New South Wales sort of geology. So it's quite close to New South Wales here. There's high alpine valleys here, which are Permian, hiding in plain sight. And we can more or less constrain the age of them because in the Triassic, a whole stack of intrusions erupted to surface and spread volcaniclastics, which are Triassic, all over this landscape. That's where the valley is, and this is where all the Triassic volcanics are, the Teapot Creek Formation. So this landscape had to be there before the Triassic in order for the Triassic volcanics to be deposited in it. So this whole region is a Permian landscape remnant. It's a sub-ice cap depression, and that whole depression is now uplifted, and it's in the heart of the Victorian Alps, and that's why it's kind of survived, because the post-Eocene erosion kind of hasn't quite made it there to start modifying it yet. It's getting close though. We're just lucky. So this whole broad landscape that turns up in the heart of the Victorian Alps is a subglacial depression, but you have to ignore these hills because they're the Triassic plugs that are intruded post-glaciation. When you look at, if we drive up into those hills to the right, you can see that the whole landscape here is a broad subglacial rise flanking the subglacial depression. It's all more or less in situ. It's just been modified a little bit by being trimmed around the edges by post-Eocene dissection, and we can recognise that dissection because all those valleys are V-shaped, not broad U-shaped valleys and broad rounded hills such as formed in the Permian. Here's another big broad-shaped system sitting in northeastern Victoria. Lots of people probably recognise this one. I'll draw your attention to this valley. Check it out. There's a profile across it. It's a gigantic U-shaped valley that separates Mount Strathbogie from Mount Samaria in the Mansfield Basin, and it's U-shaped. Now, again, like the other valleys, it's been modified by subsequent alluvial erosion, post-Eocene. But if you join the dots on this thing, it's a gigantic U-shaped valley. The entire Mansfield Basin is a broad Permian subglacial depression, and there's a couple of exit valleys for it, and one of them is the Barjag Valley, which is this one, heading further north, and downstream of this valley to the north are some Permian deposits, which give us an age constraint on when this thing must have formed. We've identified a couple of exit areas for this broad subglacial depression. Here's another one. We've got sculpted bedrock flanking the northern edge of the Mansfield Basin. It's really unusual because it's a broad sculpting all at the same angle. It's a different angle to the natural dip of stratigraphy within the Mansfield Basin, and it's way lower than the natural angle of repose for this geology. And you can see it's been modified by a little bit of subsequent erosion related to some of the small creeks there. We think this sculpting of the bedrock is Permian. It's related to an ice flow climbing up out of this subglacial depression to form another subglacial rise to the north. This is where the Mansfield Basin is. That's what the basin looks like. So the Barjag Valley is this gigantic U-shaped valley to the west, and there's this sculpted plain to the northeast as well. Now, if we have a look at the relief in this system from the floor of the Mansfield Basin to the high point nearby, Mount Buller, we're really talking about a change from the Mansfield Basin, which has been carved out as a big broad depression, to the highest points of the landscape left behind. There was a 1,500 metre relief in this Permian landscape. It's pretty amazing. It's not continuous now because a lot of the high points have been attacked by subsequent dissections. So if we zoom in on Mount Buller, it's obviously had a lot of post-Permian dissection here, to the order of 700 metres or so. And that includes some Holocene glaciation as well. There were glaciers here in the Holocene, locally, carving into these rocks to give these dramatic modern landscapes. And so, for example, you know, this is the Cobbler nearby, still gets a lot of snow in winter. Having a look at an analogue for a sort of subglacial basin of the scale we're proposing for the Permian here, we can see some in the Northwest Territories in Canada. So let's have a look in at a subglacial basin located in Northwest Territories, O'Grady's Lake. It's a sub-Cordilleran ice sheet depression. It's Holocene in age in the central Selwyn Mountains. It's being fed from a bunch of U-shaped valleys. It's got a bunch of U-shaped valleys exiting, but it's also exiting to the south, driving up over a broad sculpted bedrock plain to join into other exit valleys further south. This is actually the same scale as the Mansfield Basin geographically, and it's also got a very similar local topographic relief. This entire terrain was sitting underneath the subcordilleran ice sheet just 15,000 years ago. So we think that this is a modern analogue that actually makes the Permian interpretation seem reasonable for Victoria. Let's look into central Victoria, central West Victoria again. Permian tillite has been recorded in deep lead mines all the way along the Loddon deep lead system. Now, the deep lead system is now mostly buried underneath younger, newer volcanics. That's what those orangey pink rocks are. But underneath that, there's lots of tillite reported from all these different mines. And some of them are able to be confirmed today because the Permian till occurs on the mine dumps. So you can go there and have a look at it and go, yep, that is definitely Permian. What's interesting about this is it tells us that this is a alluvial deep lead. It's got deep lead gold in it, but that deep lead gold did not come from the Permian. The Permian glaciation is not a process that will concentrate the gold. What's happened there is a Permian subglacial valley has received post-Paleocene erosion on top of it that includes the alluvial gold. But we can see where the subglacial valley is. And we can prove its age because of all the Permian that's sitting in it. So it really shows that this landscape, this Permian landscape, is really extensively preserved across central western Victoria. And if we have a look at some of the deep leads, like some of these ones near Bendigo, some of this new understanding that it's all a Permian carved glacial landscape with subordinate fluvial landscape superimposed on top makes it easy to understand some of the curious anomalies that occurred in some of the deep lead river channels that people were trying to chase to get their alluvial gold. So, for example, near Bendigo, beneath the younger alluvium, drilling to find all these gutters that were rich in placer gold, and a lot of them were flowing to the north and to the west. But then when they started chasing them, they were also flowing to the east, and then they were also flowing to the south. This is very confusing. So people were proposing various faulted systems and various other ways of trying to understand why all these deep leads sort of seem to be flowing into a single point. Well, a simpler interpretation is that this is a Permian subglacial depression, essentially a tarn. It's more than 50 metres deep, as defined by the drilling that was all done in the 1860s through 1880s looking for the deep leads. So this is a remnant Permian feature. It got infilled by post-Paleocene erosion, which is the deep lead gold-bearing deposits, and eventually when it filled up, an exit Paleocene deep lead channel runs further north. But it's all buried under there today. And the glacial valley has been warped because there's been uplift during the Cretaceous. That's caused, related to Antarctic rifting. And so there's a drainage divide there today, which the subglacial basin is draped across. And we can see these features in other places as well. Here's another one of these weird ponding features. Now, this could be a Permian subglacial depression. I think it might be, but it is quite close to the region where there's been an uplift history change as well between the Stawell Zone and the Bendigo Zone. But so perhaps this one has been faulted post-Paleocene. And that's possible because there are places where that some of these deep leads of Paleocene to Pliocene age have definitely been cut by faults. Mostly they're reverse faults, and those faults are kind of consistent with Southeast Australia's current in situ compressive stress field. So there is a bit of modification going on as well. If we're looking far west of Victoria, there's Permian occurring underneath parts of the Otway Basin, locally in the Grampian-Staveley zone. And that's interesting because there isn't too much Permian exposed. Well, there's no Permian exposed in the Grampian-Staveley zone. Let's have a look in there. This is the Grampians we were talking about before with the little plateau remnants. If we join the dots on the plateau remnants, we can start to understand what's happened here. So this is the profile. This is that profile that I've just marked on the map. So the high point is that Major Mitchell Plateau and Mount William. The highest points in the Grampians up around 1,100 metres. There's another high point in the northern Grampians. It's called the Wartook Basin and Mount Difficult Range, up around 800 metres high or so. There's an isolated outcrop of Grampians group sitting out in the Murray Basin poking through called Mount Arapiles. It's got a little plateau on top. And if we keep extending to the north, that line just continues into the Murray Basin. Now, if we join the dots on the high points of all these remnants of what we think is a Permian glacial landscape, a plateau, and then project that line north into the Murray Basin, eventually it gets down to a point where we intersect Permian in drill holes beneath the Murray Basin, and the classic one is Netherby 1. We've got that core. That hole was drilled well over 100 years ago to try and understand the Murray Basin. There's no doubt it's there. We can image it in the seismic, and we've got the drill hole control as well. And the seismic shows that the Grampian scripts are extensive beneath the Murray Basin, but also the Permian sitting on top in yellow is also very extensive. It looks really distinctive in seismic reflection data. So we're starting to get a constraint on the fact that this surface had Permian sitting on top of it, but the Permian's been eroded away where these rocks have been uplifted at the end of the Cretaceous. There we go. So, and then the regional tilt is due to the late Mesozoic uplift and intracratonic basin sag, and that ties into the basin evolution history of the Murray Basin. It's an intracratonic sag basin related to Australia-Antarctic separation. If we have a look at parts of that uplifted terrain in the Grampians and the Wartook and Mount Difficult range is a classic one. Here's the Wartook Basin. Let's put a profile across it. It's a classic U-shaped basin. It's just absolutely classic. So we think this is glacial. It was modified and weathered during the Paleocene-Eocene, but essentially it's kept its fundamental glacial valley profile, even though there's no Permian glacial rocks left in there anymore. They've all been washed out by the subsequent erosion, and we can see the subsequent erosion where the fluvial creeks are attacking this old Permian landscape, and they're classic V-shaped profiles. And that's Mackenzie Falls in the Grampians today. That's one of the younger modern rivers or post-Paleocene river that's attacking into this older glacial landscape. It's just textbook. This is the area we're looking at the moment for the next phase 3. And this is part of a research project we're doing to try and understand the prospectivity of a part of Victoria that hasn't been well understood before. And we can use this story now to understand, much better understand, the landscape evolution that's controlling the distribution of various mineral deposits and obscuring them in central Victoria. So that's what we're using this work for at the moment, and I'll touch on it at the end. So almost at the end now, and I realise it's taken a long time, this talk, but it's good to get this narrative out there. So because of all this work we've done, we've created a new Permian to recent narrative for Victorian landscape evolution. So in the Permian, Victoria basically looked like Iceland, looks today, or Greenland. So enormous ice cap, not polar in scale, but a couple of kilometres thick, carving its way across the landscape and leaving all these features in the landscape that are still preserved quite widely today. The landscape remnants we have in Victoria, especially in central and eastern Victoria, preserve south to north ice transport directions. That's consistent with the data that's preserved in Tasmania as well, related to the Tasmania Basin. And when we look at places in Victoria on the high plains, we have features like Mount Delic, a partly eroded Permian nullitac. That's how we're reinterpreting it now. But this is giving us good confidence that this story extends into the Monero high plains in New South Wales. So they're a part of a remnant Permian landscape as well. So if we looked from the southwest at Victoria, what we had in the Permian was a sub-ice cap landscape. So we had subglacial rises, some of them were really broad, and subglacial depressions, and some of them were really broad, and they could have up to 1,500 metres of relief in that landscape. It looks something like Greenland or Canada or Scandinavia looks today. And then what happened is that subsequent to this in the Permian, starting about 90 million years ago, Australia-Antarctic separation started, and that resulted in a lot of late Cretaceous uplift. And that formed a new east-west oriented continental divide. And what we can see from the Permian story is that the uplift across Victoria was not uniform. So it was sectored. There was strong sector uplift. So far western Victoria, the Glenelg zone, doesn't appear to have had much local uplift. The Permian there has barely eroded since. So it doesn't look like it was ever uplifted. The Grampians region and the region just to the east of the Grampians at Mount Cole and the Pyrenees Range, that was uplifted quite a lot, to several hundred metres. And then east of that region, central Victoria wasn't uplifted much because that's the area where a lot of Permian is preserved, and the Alps was uplifted quite a lot. The next thing that happened was that we had deep fluvial incision of the pre-Paleocene landscape, but mainly in Western Victoria. And that involved the erosion of the bedrock and the aggressive attacking of this uplifted land surface to form isolated plateau remnants with strong erosional escarpments around them, and Whitel's gravel and equivalents deposited around the bases of those erosional escarpments. Now, what's interesting is, even though Eastern Victoria was uplifted in the late Cretaceous, it wasn't deeply eroded during this event in the Paleocene. And that suggests to us that Eastern Victoria must have been in a rain shadow at that time, and Western Victoria was in a high rainfall regime. So it was experiencing rapid erosion, and we think that that weather was coming from the west. And we think the reason that Eastern Victoria was in a rain shadow is because it was protected sitting behind this high plateau uplift that had happened in Western Victoria that was being rapidly eroded by the rain, a bit like New Zealand. At the end of that event, or towards the end of that event, there was indiscriminate in situ weathering of all the exposed geology, and that includes the Whitehills gravel and the erosional escarpments and the plateau remnants that were uplifted and the new valleys that had formed in between those uplifted plateaus in the Paleocene. And across Eastern Victoria, the Paleocene-Eocene Thermal Maximum regolith was really thick, as seen on places like Mount Buffalo and Mount Hotham, and it was uniform everywhere. But of course, a lot of it's eroded away today, but we can join the dots on the bits that were left. And towards the end of that event, there was a lot of volcanism in Eastern Victoria, and there was an eruption of all these Eocene basalts, and they copped the Eocene warm period, so they copped a bit of a regolith on them as well. And then it changed, and the reason we think it changed is because finally the circumpolar Antarctic current was able to develop, and that cooled the climate right down and polarized the climate and started to build Antarctic ice cap. And as the sea cooled down, cold sea equals cold air, and cold air doesn't carry much moisture. So suddenly the cold ocean equals a dry climate. So Victoria dried out in the Oligocene, and there's really not much erosion evident anywhere in Victoria that we can attribute to the Oligocene. It's really quite minor. So it just seems it went from super hot in Western Victoria and, well, super hot everywhere, super wet in Western Victoria, to suddenly quite cold everywhere and pretty dry everywhere. But that didn't stay that way forever. What we can see in Victoria's landscape history is that post the Eocene, Eastern Victoria has been attacked by aggressive erosion. And we can see that because the valley flow lavas of the Eocene basalts are now stranded on these hilltops, and all these post-Eocene deep valleys are formed in between those valleys, those previous Eocene valleys. And this is telling us something about aggressive erosion that's happening in the Victorian Alps and in the Australian Alps that pretty much continues to this day. Meanwhile, in Western Victoria, the Paleocene-Eocene Thermal Maximum regolith is really widely preserved still. So that tells us that actually not much has happened in Western Victoria since the Eocene. It hasn't eroded much. It must be attributed, it must be due to the fact that since the Eocene, the rainfall in Western Victoria has been consistently much lower, probably much the same as it is today. So it's just not eroding much at all. Why would that change happen? Well, we think we can attribute the start of that change to the start of the East Australian current that initiated in the early Miocene. This is the imposition of a completely new rainfall regime for South Australia that's coming from the east. And because the Alps in Victoria are in the east, now it's Western Victoria's turn to be in a rain shadow. And this is how the situation's more or less persisted to the present day. The East Australian current is warm. It's coming straight from the Coral Sea. And that's why Gippsland Sea is much warmer than Western Victoria's Sea, for example. So Western Victoria is much drier because the Southern Ocean is freezing cold and the air is freezing cold and it just doesn't carry as much moisture. Eastern Victoria is much warmer and much more humid and cops these easterly derived storms driven off the warm East Australian current. So it's flipped the erosion regime. And then various other things have happened in Victoria since the Miocene, including a period where a lot of Victoria sank below sea level. We had a marine incursion that ran in over the Murray Basin. It's the Perilla Sand. It's pretty much just draped over the top of this story. And then there's neovolcanics, which continue to erupt almost to the present day. And they're probably related to far field stress effects from New Zealand as well. So with this much more constrained landscape history, we can start using it to think about various aspects of mineral exploration that might have been misinterpreted in the past. And so, for example, prospectivity targeting, example for gold. So here's our landscape history. And what we can see is that there's areas where there's been limited post-Permian erosion. And there's been areas where there's been extensive post-Permian erosion. And the Alps is one, and central West Victoria is another. Now, once we have this nuanced understanding, we can start to understand why using Victoria's placer gold deposits, which are all Paleocene to Oligocene in age, as a proxy for estimating the potential of the bedrock to host gold. So using Victoria's placer gold deposits as an estimator of what the endowment might be in the bedrock underneath is more complicated than just using a blanket approach in Victoria. So in places where there's been a lot of post-Permian erosion or post, whether it's in the Paleocene or the Eocene, the placer gold endowment of those areas is giving an indication of the primary gold endowment of the bedrock underneath, because there's literally been hundreds of meters of that bedrock eroded to contribute gold, orogenic gold, to the placer deposits that are now sitting on top of them. So if you find areas where there's a lot of placer gold, you can use them as a bit of a vector to sort of hunt down the areas of primary gold that probably fed those placer deposits. But this method falls over in areas where there hasn't been much erosion since the Permian, since glaciation does not concentrate gold into placer deposits, it disperses it. The only thing it concentrates are really strong minerals that can survive the aggressive erosion beneath an ice cap. And an example of that might be diamonds, for example, which is why diamonds occur in places like Beechworth in Victoria in the Permian. So why this is important is it helps explain the dichotomy between places like Bendigo, which has the highest gold endowment, primary gold endowment recorded in Victoria, but doesn't actually have a really rich alluvial gold history. And we think that's probably just because there hasn't been much erosion at Bendigo post-Permian. And the proof of that is the fact there's still Permian tillite scattered around near Bendigo. Whereas south of the drainage divide, Ballarat has experienced more erosion. It's lost its Permian, and it looks like there's been another couple hundred meters of erosion there, which is why the Bendigo goldfields are a fantastic placer goldfield, and the hard rock endowment doesn't seem quite as high. It's particularly important for the Melbourne zone, because the Melbourne zone hasn't got much alluvial gold at all. And with this new story, we understand why. There's been virtually no erosion there since the Permian. It's remarkable how stable it's been and how little eroded it has been. So there could be significant primary gold deposits in the Melbourne zone, and we think there might be. And the fact they don't show up in the placer deposits doesn't rule out their existence. So that's pretty much the end of the talk. Thanks for staying for a wild ride.
That was quite the ride. Thank you very much, Ross. That's excellent. Now we have a few that have stayed on right to the end. That was such a great walkthrough and way more than we got at the ARGA webinar. So thank you so much. Right, I will start. Okay, Mike's got a question sitting right here. I'm going to ask him now. Well, it's in my head too. Why do you think the East Australian current only got going in the Miocene? The Tasman had been open for some time at that point.
Yeah, that's a good point. So the reason I've gone for that is because that's the conclusion of all the people who studied it, basically. So we think it might have got cracking a little bit before that. I'd be pretty comfortable with the idea that it might have started getting cracking at the end of the Oligocene. If I was going to predict when that current started from the story we've got in Victoria, that's what I'd say. But I can't find any modern papers that say that. So I've just gone with the papers that I could find. So if people want to argue that it started before that, I'd be more than happy, because I think the earlier it starts, I don't think it would start during the Oligocene, for example, because we don't see any reflection of it starting in our story. Well, yeah, we could accommodate the Oligocene actually, but it's probably not the Eocene. So then that would fit the idea of how New Zealand Tasman Sea opening and stuff fitted.
No, it's great. I guess if anyone finds any articles that Ross could use to push that back, then send it in.
My way. Yep.
Awesome.
I guess you've got the evidence, you just need the cause.
What was that? Sorry?
you've got the evidence, and now you just need the cause.
Yeah, that's right. So it's interesting, isn't it? Because when you have a look at, when you have a look at that great escarpment in New South Wales, you can see, that's eating into the eastern edge of the Monero Plateau there. It hasn't actually retreated that far back from the coast. It's just not that old. It just can't be. And I think we've got the story in Victoria that tells us how old it is. It's going to be post-Eocene and possibly, Oligocene or Oligomycene. I mean, it could be in the Oligocene, I reckon, but I don't think it's certainly not in the Eocene. Because Victorian alpine erosion prior to the Eocene was really minor. It was just a couple of spots where it happened, and one of them was near Buchan.
So have you got any good papers pointing to about the PETM? It's something I'm not familiar with. I mean, it explains a lot from what I'm looking
yeah, I mean, there's a lot of papers around. So, I mean, I just pretty much just let Google be my friend to get my hooks into that as quickly as possible. And I quickly got myself into the literature just by Googling PETM. So Wikipedia comes up with a bunch of good root papers, and then once you dive into them, you get a whole bunch of other ones as well. So it's funny, because the Paleocene-Eocene Thermal Maximum has really only been written about for the last 15 years or so, I guess. And yet in Victoria, everyone's known it was a thing from the mapping forever. It's so well constrained.
Absolutely.
And if we'd pulled our finger out, we probably could have almost done the global definition of what it is, because it's so well preserved in the landscape, and it's so clear what its age is, because the Whitehills gravel is Paleocene. It incorporates fresh bedrock into a high energy fluvial gravel, and that bedrock is completely weathered. So it couldn't possibly have been weathered when it was incorporated into the gravel, because it would have just disintegrated. So that straight away tells you that all the weathering you see superimposed in the Whitehills gravel is superimposed. And then the next thing that happens is it's cut by these deep lead river valleys, which are Oligocene, and they've got Oligocene palynology. And the Oligocene river gravels rework the Paleocene-Eocene Thermal Maximum regolith into a mix of kaolinite and weathered fragments of laterite and reworked Whitehills gravel fragments and some fresh bedrock fragments as well. So the fact that the Caliban Formation has fresh bedrock fragments incorporated into it proves that the regolith couldn't have overprinted that, because it wouldn't have the fresh in there. So it's just so well constrained. It's amazing. And we had this story, and yet there's been these wildly different stories for the uplift and erosion history of the Alps in the literature. And partly it's because of this difficulty of tying what's happened in the Alps to what we can constrain happening in Western Victoria. So people just treated them like completely separate things. And when we started diving into it, we were doing that too. And the key breakthrough was recognising the Permian part of the story. And the reason no one's proposed the Permian part of the story is because it's just so preposterous that there's 1,500 metres of relief in the Permian story still preserved in Victoria. It's astonishing. And the fact that some bits of it look so intact means it must have been protected under Permian deposits, and they've just eroded away much more recently. And the underlying bedrock landscapes emerged. It still hasn't yet been attacked in some places. It's remarkable.
Awesome, thank you. And I've got one more question from Leah in the chat as well. Do you know what the paleo scale direction was? Any thoughts on whether this was an old view, one large LPIA ice sheet, or emerging view, smaller continental ice sheets radiating out from smaller centres?
Yeah, that's interesting. Look, we're not really sure. My gut feel is it was probably one large ice sheet actually, and I think it gets more complicated as you go north, but it does continue into New South Wales in the Ovens Graben. There's a lot of Permian preserved in drill holes in the Ovens Graben, and looking at the Monero Plateau, I don't see the geomorphology of it really changing until 150 kilometres north of the Victorian border, sort of thing. So my gut feeling is that at its maximum, it was probably just an ice sheet a couple of kilometres thick that just went across the whole of Victoria pretty much and just scoured the whole thing. And then, of course, as it started to melt, it would have collapsed into a series of smaller ice tongues and become more complicated. And we see that in the history because there are all these subglacial lake and fluvial glacial system deposits as well, and they tend to be towards the top of the stratigraphy. And there's been a lot of work done on those around Bacchus Marsh. There's a lot of stratigraphy preserved there. There's quite a lot of fluvial glacial stuff sitting on top of the subglacial tillites. And there are some subglacial tillites. So we have some Permian tillite that actually has Permian glacial surfaces carved in them. So we know there was ice over the top of existing tillite. Some of it was sub-ice cap tillite. And the good thing is all that work's been done. It's been painstakingly documented at individual sites. What was missing was the overarching story to recognise some of the really big features that don't have Permian in them anymore, but you can still kind of more or less prove they were Permian. And the classic one is the Benambra one with the Triassic volcanics in it. Now, we know that landscape's at least Triassic. So, and we haven't had time to go and check yet, but we suspect that there's probably Permian tillites associated with those Triassic volcanic classics. It's just that when they were mapped, no one was expecting to find them. And there are some historical descriptions that sound a bit Permian there from some of the old alluvial mines that were happening around Omeo and stuff. So there's always more work to do with these things.
Yeah. Leah's chucking more stuff in the chat here. We could be here all day talking about this. I love it. She just said that it's interesting because the data from the West Australian Shield suggests several ice sheets that radiated, but next door in SA, there's 5 to 7 kilometres of ice and one large ice sheet from Antarctica. So interesting.
Yeah. Well, and look, Tasmania plays part of the story as well. So
yeah.
So Tasmania, the Tasmania Basin's a mix of tillite and fluvial glacial stuff. I think that the current thinking is that some of the Tasmanian highlands weren't completely inundated by the Permian ice cap, but it's hard to tell because the Tasmanian highlands got absolutely trashed during the Holocene glaciation. They had an ice cap on them then. So I don't know how you'd even recognise if there was a Permian one on top. I can't help thinking that given the relief we've got in Victoria, there's actually more relief in Victoria than the highest peaks in Tasmania. So it's possible they could all have been drowned underneath the Permian ice cap, I think. I think it was more just the idea that it's just hard to imagine that there could be that much relief in the system still preserved.
Yeah. Mike's proposed that every state and country needs a Ross Cayley.
Oh, well. I mean, it's funny, isn't it? Because I quite like, the thing I like about these sorts of stories is the systematic building up of criteria that constrain things, and they can just lead you to somewhere preposterous in the end. I've always wondered about what Mount Macedon was. I was thinking, it must just be a remnant of, one of these Cretaceous hills. It's about the same height as, Mount Cole. I guess it must have all eroded away. And you can see in all our map reports, everyone's sort of skirting around this problem. And so one of the things that people have done with mapping Permian in that part of Victoria was having all the little bits of Permian faulted. So you just draw faults around them all. And so then they suddenly become these little mini grabens all sort of, and that disconnects the Permian from the landscape it's sitting in. And that's what's happened. So people have mapped these things, have done a good job mapping them, and then they've put faults around them as a default because it seemed preposterous that the whole landscape across central West Victoria is a Permian until you go to the places where there can be no question that Lake Epilog's a Permian landscape. You've got these carved bedrock glaciated surfaces, and there's all Permian in situ on top of them. And then when you start using topography to map away from them, you realise that actually, do you know what? It's all bloody Permian. It's just been in places, it's been incised, maybe a few tens of metres by creeks since then. And so the fact that that's so intact after 300 million years tells me there must have been a lot of Permian tillite across the state, and it just protected this landscape for a lot of that time. And a lot of it's gone now, but there's still quite a lot of it left. And as soon as you see places where it's still more or less not so eroded, so for example in the Ovens Graben and beneath the Murray Basin, it's hundreds and hundreds of metres thick. And so how do you get hundreds of metres of till everywhere? Well, one way is to have a pretty thick ice cap that's carrying distributed material all through it. And then as the ice cap fails, all that distributed material just concatenates into a single deposit at the end. And I think that explains a lot of, the widespread nature of the tillite we've got here. And it'll be interesting to do more drilling under the Murray Basin one day. I mean, the seismic suggests this stuff's everywhere.
Yeah.
The thing about, for Victoria, one of our projects for that Minix Phase 3 area is to try and understand where the Permian is and where the Permian isn't, because gold explorers absolutely hate it. It's terrible stuff to drill through. And obviously, geochemically, it completely masks the bedrock underneath. So you can't make any estimations about what's going on underneath. And also, the worrying thing is there's 1,500 meters of relief here. So where's the bedrock go? So we're trying to come up with tools that can estimate how thick the bedrock is underneath, so explorers don't just give up when they get to the Permian, because that's what normally happens. And by characterising the landscape around Bendigo and Heathcote, I think we've got to the point where a lot of that carved Permian landscape really only has about 50 to 100 meters of relief mostly. So, it's probably not the end of the world if you get into some of this Permian stuff, if you're prepared to drill 50 meters or so, you probably get through it. But, we're still looking at tools to try and do a better job of that, because that's what's really held back exploration of the northern Melbourne zone. And antimony is a critical mineral, and the Melbourne zone's got a lot of antimony in it. And it's half unexplored because of this. So, we're interested in trying to move the dial on that and see if people can find a way of exploring through this stuff. And step one is understanding it. So that's what this work's been about.
It's fantastic. I think that's a really great reason to perhaps start wrapping up, and just thank you so much, Ross, for your talk, because as you say, this is such an area that needs the work, and I think it goes back to the power of just getting on the ground and following up in regional surveys, like Mike's pointed out, that a lot of the regional survey work has really got you out there and looking at these big structures and looking at these big regional areas, but then also going back to those observations and that other people have done as well, and just pulling that all together. So that field mapping component is so important in pulling together the story, I think.
Yeah, well, on geology, it takes a village with geology, doesn't it? I mean, a lot of the stuff's not really my specialty, but it becomes your specialty, right? Because you're just kind of forced to sort of dive in and get stuck into it. But these are the reasons why I still do geology. It's awesome, right? Because
there's always something to learn.
Stories just popped out from nowhere, and it's fantastic.
That's great. I think it's definitely got a few of us in South Australia thinking about some opportunity.
It makes me wonder. Yeah, it makes me wonder about the supposed Cretaceous age of the glacial features around Arkaroola.
Yeah, well, it's one for Steve Hill, that one.
Yeah, I know. That's right.
In Steve Hill. But yeah, I mean, because that's a lot of that they've got the glacials that the Reading Ridge Bridges, that are actually glaciers in the work that Neville and Steve have done, and the Bulletin 57. Yeah, it's Cretaceous, but I mean, maybe it's just a little slightly offset there, or who knows. So interesting. Lots to learn. Okay, thank you so much, Ross, and thank you everyone for sticking around to the end.
Yep.
We will have this up online once we get it sort of figured out, probably the next week or so. And yeah, we really appreciate your time, Ross.
No worries. Yep, awesome.
Just learned so much today, so it's great. And look forward to the next one in May 14th, I think. Check it out on LinkedIn. People want to join the group, you'll get first dibs. We have a Facebook group, we have LinkedIn, we have our YouTube, which is tucked in the links too. Get in touch.
Yep. Excellent.
Awesome. Thanks, everyone.
Thanks so much, Ross. That was awesome.
Oh, thank you. See ya.
Yeah, it was awesome. Thank you.